The following program is brought to you by Element 14, the electronics community where you can connect and collaborate with top engineers from around the world. Join now at element14.com/presents.
I've got a project for you.
Okay.
Amazing hacks. Inspired designs. Each week, Element 14 Presents brings you innovative projects using electronics, engineering, and more.
Welcome back to Element 14 Presents. I'm Clem, and in this episode, we're building an RC remote control from scratch, and I mean from scratch. A while ago, my buddy Goofy visited me in my shop, and we talked about his RC crawlers. I'm also big into RC crawling, and he's even doing competitions with them. And we got the idea about building a completely open source, open protocol RC remote from scratch. And this is basically a follow-up to a previous episode that I did where I've built a custom remote for an RC car from a PS1 steering wheel. The link is in the description below if you want to see that episode. And in that episode I used the Arduino MKR to build an RC system, and this time I want to address some questions that people had on the Element 14 community. Mainly, can you do that with an Arduino Uno? Do you have to have expensive microcontrollers for that? Or could you do it on the bare bones thing, like an Arduino Uno and a Wi-Fi chip, for example? And that is what we are trying out today. To develop the hardware, we're using an Arduino Uno, as discussed before, an ESP8266 module for the radio communication, so we're using 2.4 GHz Wi-Fi, and on the other end, the same thing, an Arduino Uno and an ESP8266 to receive the transmission and actuate the servos of an RC model or whatever you would like to remote control. I already hear you typing furiously in the comment section. Yes, you could do all these tasks with just a bare ESP32 or even an ESP8266 module if you have the right one, but I want to be restricted. I want to find out, can I do that with minimal hardware? I only have ESP01S modules. These are the ones with very low I/O and 80 mega 328Ps here. So this should answer the question, can you do it with an Arduino Uno and just a bare Wi-Fi module? And is it really necessary to go the 32-bit route to accomplish that goal? This is the very first iteration of an open source remote, so I made some custom hardware that allows me to test a lot of things. I want to know how many channels can I transmit without running into trouble. So I want to read a lot of inputs. And I'm using some shift registers that I used in projects before. I put them on a custom PCB that I designed in KiCad. I'm reading some switches, some momentary push buttons for the trimming, and also dip switches. So I know I can read different types of input and transmit them over Wi-Fi to my receiver. On the board there's also a connector for an I2C OLED screen, because I want to know, is attaching an OLED and driving it decremental to the latency? Does it take a long time to draw some fancy graphics? Or doesn't that make any difference? Because the I2C device is a microcontroller device in itself and does it on their own? Let's find out. And I also tried to make self-centering servos with a mechanical design that I did in Fusion 360. So all the shell and all the mechanical components of this RC controller are also completely custom made and not based on any existing design. So I used a spring kit that I got from Element 14 to find the perfect springs to make self-centering servos. And that turned out to be doable, but the self-centering is not very reliable. So I think I have to do a lot of iterations until I get a working design. I would prefer to have ready-made self-centering servos, but I couldn't find them so far. As with a lot of projects before, Isla.net is providing the PCBs for my project. So thankfully, I've got a partner on my side that does a great job on delivering these PCBs in time for the project. It takes a lot of time to design all these things, and especially for all the CAD, for the mechanical design. I really like the export feature of KiCad to have step files that I can put in Fusion 360 and then export a DXF from Fusion 360 and re-import that into KiCad to make sure that my PCB and my mechanical design will match. And in case of the remote receiver, they match so good I can't get the PCB out again because it fits, like snuck in there. I'm using the Arduino Uno only as a development kit in this project, and then I transfer over my code to a bare ATmega 328P chip. If you want to know how to migrate your project from a full Arduino Uno to just a bare chip, there's a link in the description for a project where I did exactly that. Let's take a look at some code segments. I can't show you all of that because that would take too long, but here are some interesting sections that I used and some that I pulled out again because they introduced too much lag. Here is part of the code that is running on the ATmega 328P mounted on the remote. A lot of these functions are not used in the final product to avoid latency, but some of them might be useful for further development, so I'm only showing you the interesting ones. So we of course declare all the pins, have to set up a lot of values. The first thing we need to know is the serial begin function to communicate with the ESP8266, and we tested everything with 9600 baud to make sure everything works. The maximum baud rate that I found that worked to have a successful transmission is 11500. In our loop we do all these procedures. These are all written in their own functions. First we read the shift registers, then we read the analog inputs, then map that data to the real variables. Trimming is reading the push buttons that we have read with the shift registers and applying those values to trim values for the analog outputs. We apply those trim values. Then we have a lot of test functions for development. We build a packet that gets sent to the ESP, and then we send that packet. These display functions are used for the OLED. To read the shift registers, we use this function that's basically the same code that I used in previous projects. The analog inputs are read and mapped to a value of 0 to 180, but we need to have a different range of movement. So I found these values by try and error, and then I remap them to my range again. So I make sure that the resulting function is always within that range, and also this function catches all the errors that may lead to a minus value on some of these analog readings. So if some of these would result in a minus value, a negative value, we go to this function and do it again. This is the map data function. We are reading a value from the shift registers that is stored in a variable called parallel data, and then we match every digit of that parallel data to a certain variable. And after that we can use those variables for further functions. This is the trimming segment. So if the shift register registers a low signal on a trimming button, then the trim value will be incremented or decremented depending on the button. I also designed a little update function for these values to be stored in EPROM, so if the remote control gets restarted, it could read back the old values and you don't have to trim again, but I haven't finished that function, so it's commented out for now. Also, this takes up time that adds up to latency. Here we have the apply trim function, which is basically using the analog outputs that we have processed plus the trim values and generates a usable output. Then we build the packet in this function. We need to have 3-digit values no matter how big that value is. That means if a value is under 100, we have to add a 0 because it's only 2 digits long if it's below 100. And we have to add another 0 if it's below 10. You may want to add 2 zeros if it's below 10, but keep in mind if a value is below 100 and it is below 10, it would add 3 zeros in total. So in that case, if we add only 1 zero per case that is positive, it will never add too much zeros. I discovered that in debugging, of course. Then we built that packet and put one value after the other in a determined sequence. So the microcontroller, on the other hand, will know how to decode that. And then we send it with a serial print line command to the ESP.
Hey, how would you like to get free stuff like this? The Element 14 Road Test program sends you free products in exchange for detailed reviews posted to the community. Head over to element14.com to see past reviews and apply to be a road tester today.
We also have a lot of functions that deal with the OLED. The OLED is an I2C device and we're using an Adafruit library for that. So we use that to generate the signals. Also on the trimming function, if a trim will be done, then we have this draw character function that allows us to display the channel that has been trimmed on the display, so you know which button you have pushed. The AVR has sent over the packets to the ESP on the transmitter side. We establish a Wi-Fi connection with the ESP, so we need all these variables to set that up. On this side, it's a Wi-Fi access point called Trailbug Remote, and the other ESP will access to that. So we need to have it set up. We need to wait for it to be valid, and then we begin UDP transmissions. Our maximum baud rate that we found in the other code has to be matched here. In the loop, we have a safe reading command. This is basically reading from the 80 mega 328p, and then it uses the incoming value that is called incoming in this case, make it to a packet and send that packet over UDP. Don't waste any time with any other processing. In the safe reading function, we have a lot of checks in place to make sure that is a valid function. But on debugging, I found out that if I move those checks to the other side, it reduces a bit of latency. There's also a separate send UDP function. I found this to be quicker, but I can't explain you why that is. Maybe the latency comes at some point that I can't really determine. We're now at the receiver side, the ESP8266 on the receiving end. This one has basically the same credentials, but we set that up as a Wi-Fi station, so it will only access an access point, and we have to wait until that connection is established. A handy little feature that I did in the setup loop is I wait for the connection to be established, and then I pull up this pin ready flag that gets read by the AVR, and then it knows it can start the transmission. On the other end, it's the same thing, and by coincidence or by careful planning, ready flag is also connected to the onboard LED of the ESP8266. So if that module is ready, I can tell by the LED. We are reading the incoming packets with this function. So we parse the packet, and if the packet size is not nothing, there is a packet, we read it, make sure the packet is long enough, and then we serial print that incoming packet as it is to the Arduino on the other end. So the 80 mega 328p can read that. And we also have to make sure that it has the right terminator. I set the 8 mega to wait for a new line signal, and that it is. If you would use serial print line, it would send a new line and a line feed character or a carriage return character. So I made sure that only that one occurs to be able to make sure the transmission is correct. And then we flush the UDP to make sure we have room for the next transmission. There's also a safe reading function for testing and a lot of other stuff that doesn't really make it better, so I commented all these functions out. We are now at the receiving end of the AVR program. On this end, we have to include the servo library because we want to move some servos. Of course, we declare all the pins and variables that we need. And this time, the maximum serial value is 57600. That's the highest speed the AVR can read from the UART when it's running at 8 MHz. It might be higher when we run it at 16 MHz. I tried that in like a dry run without reading it with a microcontroller, just transmitting from PC to PC. It didn't turn out to be that quicker. We have a lot of functions that are commented out because they added a lot of overhead to that. And the thing that I want to be as fast as possible is servo movement. So when the module is activated, we center all the servos and then we wait for the ready signal from the ESP to go low. Also the LED on the board goes high, so we know that has occurred, and then we start the loop. On the loop, we read the incoming string until the termination character that we have determined. These are some validation checks. We only use one of them because we're waiting for a 21 character array, 20 characters plus the null terminator. And if that is not correct, we know that the packet is either incomplete or it's corrupted or somebody sends garbage data. So we only use usable data. Then we map those packets digits to the functions. These have to have the same order as we determined with the packet on the other end, so we know which is which. This is for all the switches that we didn't incorporate on the receiving end because that also takes up a lot of time. To make it a little bit more snappy, then we have this function that checks for validity of the values, and if it's not, it will discard the values and wait for new ones. We have a lot of security things in here. Also, this should shift out the data for the digital outputs, and that also takes a lot of time, so I commented that out to make sure it is faster. We want to have a usable remote in the end, and there is also a failsafe function that makes sure if there is no valid signal for a certain time, it will reset all the servos to a safe value. My RC remote control from scratch is finally ready. It's pretty ergonomically, so I can reach all the analog inputs with my hands without cramping and can control them all pretty good. It also has a lot of these digital I/O. Let's put the receiver into some RC cars and try out if this is a usable remote control that's based on Arduino Uno, basically. So this is my homemade RC system based on Arduino Uno. I've proven two things. First, the developers of remote control systems pour a lot of money and effort into their devices. So there's a lot that goes into building a reliable remote control. That's not an easy task. I've also proven that yes, you can build a remote control based on Arduino Uno, but is this a good idea? Not so much. While it works, it has latency problems, and the more communication points you have, the more latency gets induced. Also, a 32-bit platform is the way to go these days, and with some of the microcontrollers that are available today, for example in the Arduino MKR Wi-Fi, it's not as expensive as it used to be. So for a second iteration, I would definitely switch to a 32-bit microcontroller platform. If you have any ideas for more projects that we can try out, like rebuilding something commercially in a DIY fashion, or any other project ideas that you have, post them on element14.com/presents. I gotta go, there's another project waiting for me.